Okay, so I guess since most of you, like I said, have done the basic QCQI course that was offered last semester, you know the drill. I will be writing on the notepad and I will upload the handwritten notes as PDF onto a Google Drive folder. I will be recording my lectures. I will also upload the lecture recordings in the same Google Drive folder. Let me just pause to say that we have 2 TAs for the course and both the TAs are around today, I think. There's Gautam. Gautam, you just want to say hi?
Yeah. Hey guys. What's up?
And there is also Debjyoti. Is he here? Debjyoti is not here. Oh yeah, he's here. Okay. Just say hello, Debjyoti. That's all. Yeah. Okay. Cool. Yeah, I mean, there was some thought about whether we should make this an in-person course and things like that. I don't know how many of you are on campus, frankly, but at this point, the situation is certainly not conducive to doing anything in person. So we will stick to this format of virtual lectures, which will be recorded and uploaded. Perhaps sometime in February, the situation eases out. And if there's, at least half the classes on campus, we can try to do 1 or 2, meetings amongst, the students, maybe with the TAs. At least one of your TAs is on campus. So we could try and do something in person in the second half of the semester, if at all possible. Okay. Let's assume we tide over this wave soon enough and we can do that. Okay, so before I get started, any questions on the logistics of the course? Are there any issues? Is everyone able to access Moodle?
No issues, ma'am.
Okay, cool.
Ma'am, will we get any practice sheets as such?
Sorry?
Will we get any practice sheets?
Oh, yes.
Sheets?
Sorry. Indeed. Yeah, indeed. Good. I'm glad you asked. So yes, we'll certainly have, I will certainly put out assignments, okay? And we will have tutorial sessions by Gautam and Debjyoti. By the way, their contact details are on Moodle, okay? So in case you want to reach out to them, please do so. So Gautam and Debjyoti will probably create a WhatsApp group for the class as well. And they have all your email IDs and stuff, at least also registered on academic, whatever list I have, the enrolled list. They'll probably circulate something for a WhatsApp group and then you can all join that. So we will have assignments which will not be weekly, okay? My assignments tend to be whenever I finish one module or one chunk of a topic, right? Assignments will not be graded, okay? I will put out assignments for you to practice, but they will not be graded. There will be tutorial sessions where you can discuss the assignments and the solutions with your TAs, and we'll also try to upload solutions for the assignments. There will be a mid-sem, which will probably be sometime towards the end of February or early March, and this will be worth 25 marks. There will be an end-sem, which will be worth 50 marks. But I would like to do term paper plus presentation on some research topic, right, that's associated with QCQI. It doesn't even have to be something that I necessarily cover in this course, right? For example, I will not delve deep into algorithms in this course, right? So this will be worth 25 marks, okay? So like I said, the term paper plus presentation can be on any topic of interest for you guys, right? But it just has to be current or mostly current research. Should not be something very old, which is like something which is, discussed as a theorem in class or something. It just shouldn't be something that old or pedagogical, that's all. Okay, so what will this course be about? So let me just briefly mention the course contents. So the first module or the first chunk will be to understand quantum noise channels. Okay, so the logic being that we have seen, hopefully we have seen, the power of quantum computing and quantum information processing in our basic QCQI course, right? So then what prevents us really from just building a quantum computer today? Why don't we just see plenty of quantum computers around, or why don't we just see plenty of, you know, quantum networks around which do quantum cryptography and stuff? So what is the biggest bottleneck in realizing the potential of quantum computing? The answer is this noise. And this nature of this noise, as with the nature of the information, is very different from the classical case. So the first couple of weeks, we'll focus on understanding what quantum noise channels are. And then we will try to understand quantum error correction, right? Which is, how do you protect your information from the effects of this noise, right? That's the natural next question. Once you understand the nature of the noise, the next question will be, how do you protect yourself against this noise? So that's quantum error correction. And then, so these are the big chunks of this course. The third big chunk will be on what is often called quantum Shannon theory. Okay. So this will be about understanding. So we've understood how to store information in quantum states. And with quantum error correction, you'd have been understood how to encode and decode information, how to store it in a way that it doesn't get corrupted. But one missing piece of the puzzle is, how do you communicate using quantum states? That is something that we did not touch upon in the last course. We talked about how to compute with quantum states, but we didn't really talk about communication, right? And that's where Shannon theory comes in. So the idea is to understand the basic tools needed to understand quantum communication or quantum communication networks, right? Along the way, there's a couple of little modules that we will do, one of which is on entanglement theory. This again is something which, although we did spend some time doing Schmidt decomposition and so on, but we didn't really talk about entanglement measures. We didn't really talk about mixed state entanglement. So this will be one short module. And these will be important tools actually to understand quantum Shannon theory, right? How do you quantify mixed state entanglement and so on? Because after all, the Schmidt decomposition that we did only talks about pure state entanglement, right? And already maybe many of you have even forgotten what Schmidt decomposition is. So let's revisit entanglement theory a little bit before we do quantum Shannon theory. And again, if time permits, right, we might do a small module on quantum optical states and communication, but this is only if time permits, right? So this is very optional. Rather, how do you compute or store quantum information using optical states, and how do you communicate with them? So that's sort of what I mean by this vague heading. But 1, 2, 3, 4 will definitely be covered in this course, right? And the rest, yeah, we'll kind of see how far we can go, right? Quantum error correction itself will form a pretty big chunk. Quantum Shannon theory will form another piece, okay? And the others will be short modules around it. Okay. Any questions? Fine. So I have already put up some of these modules on Moodle. Okay, so you can go take a look. I have put up references also. So for the first couple of weeks, like I said, our focus will be on understanding quantum noise channels. But I've titled this lecture as quantum operations, right? Why is that? So when I say quantum noise channels, so the kind of picture that conjures up that you should think about is, I have my density matrix rho. Okay. Again, I hope everyone remembers what a density matrix is. Can someone quickly tell me what is a density matrix? So let's say we're talking about a d-dimensional quantum system. What is a density matrix? Okay, it is a matrix. Let's say it's a d cross d matrix But what kind of matrix is it? What kind of operator is it? Just please unmute yourselves and answer. I'm sure you have the ability to do that.
Hermitian.
It's Hermitian, yes. Okay. Which means row adjoint is row. So it's a Hermitian operator or a Hermitian matrix. D cross D. And what else?
Positive definite.
Very good. It should be positive semi-definite. So this is how I will write it. So this means that it should be, oops, positive semi-definite. Positive definite would just mean that there are no zero eigenvalues. Semi-definite would mean that there could be one or two zero eigenvalues. That's okay. Right? Is that it? Anything else for a quantum density matrix?
Trace
Sorry?
trace has to be 1.
Very good. Okay. Otherwise, I was wondering if I have to now do a review on basic QCQI. Okay. Someone's saying something on the chat. Can you just speak up if you can?
It's a superposition of all those pure states, right? With their probabilities of occurrence.
Exactly. Yes. That is one way to think about the density matrix. But I'm now talking about the density matrix as an abstract mathematical object, right? As a mathematical operator, it is a Hermitian matrix. It is positive semi-definite. By the way, the fact that it is, do I need to state both these conditions separately? Hermitian and positive?
Positive semi-definite is sufficient, right?
Correct, because that would imply that it is Hermitian. Good. So if any of these statements seem like, they are, coming out of the blue, then please go back and revise this, right? So a positive operator, how do you define it? Okay, so I'll just do a quick review of these things because it's very important that we start on the same page. So how would you define okay, so let's say that these are the two properties, defining properties of a density matrix. Okay, that it is trace 1 and it is positive semi-definite. And I've told you that positive semi-definite implies Hermitian. Okay, now what is a positive matrix or a positive operator? How do you define it?
Expectation of any pure state with it is positive.
Correct. So another way of saying it? How would I check that? Okay, so the idea of a positive operator is that the expectation value with respect to any pure state, let me say phi, is positive. Correct. So I give you some D cross D matrix. Okay. So what does this mean? This means phi rho phi is always positive, right? That's the same as saying that rho is a positive operator or a positive matrix, right? Now, how would we check this? So if I give you some random 2 cross 2 matrix, how do you know whether it's a valid density operator for a 2-level system?
Its eigenvalues have to be positive, also non-negative.
Exactly. Yeah. So these two conditions are again the same, that this happens if and only if the eigenvalues of rho are positive. Again, we can say positive semi-definite. Okay. So these are if and only if statements. And these are all things that you would have done in the very first assignment of your basic QCQI course. Okay. But I will include some of these questions, especially since there's some of you who have not done the QCQI course just the last semester, but probably have done it 2 semesters ago. So I will give this, let's say, as an exercise in your assignment. to show these properties about positive operators. Okay. Okay. So let's just revisit some of these things again. So what is our description of a general quantum state? So a quantum state, we say typically, so let's say this is again, I'm talking d-dimensional systems. This is an element of CD, right, which is d-dimensional complex linear vector space. So states are vectors in a vector space, right? Should I qualify that a bit more? Is it any vector in a complex linear vector space? Is there some condition?
Normalize.
It should be normalized. Yes, good. So this should be a unit vector or a normalized vector. Same meaning in a d-dimensional complex linear vector space. Now this description is not the full description of a state because this describes the so-called pure states, right? So a pure state would be described as a vector in a vector space. But as I think Siddharth was the one who pointed out, you can have what are called mixed states, right? And mixed states are essentially convex mixtures of pure states. And in the previous course, we have seen several scenarios, examples. We went over this. Actually, we spent quite a few lectures, I think, on discussing this idea of mixtures of pure states. One common scenario where they arise is in a measurement, right? If I input a pure state to this measurement box, so you can think of this box as something that is executing a measurement, right? I'm revisiting this because a measurement will be the first example of a quantum operation that we look at, okay? So a measurement, what does it do? It gives you, so let's say you're measuring some Hermitian operator A, right? This is an observable. Remember, observables are Hermitian operators. So we are measuring some Hermitian operator A, then we get one of a set of outcomes. And depending on which outcome you get, you end up in one of the eigenstates of this operator, right? And how do I describe this post-measurement state? So this is the simplest example of a physical scenario where you get a mixed state, right? You take a pure state, you measure it, and then you end up in one of the eigenstates of the operator that you measured. That's the post-measurement state. Now, if you know what the outcome is, you can say that the transformation was essentially a collapse, right? That it collapsed the pure state psi into a different pure state depending on which of these outcomes was realized. But if I want to describe the post-measurement state without reference to the outcome, right? If I want to describe the measurement as a process, right? So if I want to describe the post-measurement state, then we would describe it exactly like this as a convex mixture of pure states, because each of these outcomes get AI, which are the eigenstates. So these are all eigenstates of this Hermitian operator, right, is realized with a probability Pi, right? And of course, sum over I Pi is 1. This is a probability distribution, and each of these lies between 0 and 1. So this is how you would describe the post-measurement state. You would say that measurement of A transforms my pure state psi into this mixture, right, into a probabilistic mixture. And that's why I called it a convex mixture as well, because this is a convex combination of the eigenstates, right? Now, the concrete way to describe it, of course, is in terms of these so-called outer products and all that. So just a quick recap, like I said, of what we did last semester. So the pure state psi itself can be described in terms of its projection, right? The projection onto psi is this operator with the outer product psi, right? And the measurement transformation will be described as sum over I, EI, projection onto each of these eigenstates, right? So these are all projections or projectors onto the different eigenstates, right? So this is now a transformation from one density operator. So I will call this rho sub ket psi, okay? To indicate that this is the density operator associated with a pure state. The density operator associated with the pure state is simply this outer product, right? Remember, this outer product is a matrix or an operator because it's multiplying a ket with a bra, right? Which means you take, if you visualize this, then it's a row vector multiplied by column vector. So it should give you a D cross D matrix. You can check that this has all the properties of the density operator that we wrote down earlier, right? Namely that it is positive semi-definite and it has trace 1, right? Remember that trace of this outer product can be easily written as simply the overlap of psi with itself, right? These are all tricks we learned last semester, and this is equal to 1. Recall this, and if you do not know this, then check this. Check this by using the definition of trace, right? And make sure that you understand this. Okay, so now this initial density operator, which was simply the density operator associated with the pure state, has become this density operator. Let me call this sigma, which is equal to sum over I, Pi, outer product, AI, right? So this is one way to understand why we have to talk in terms of density operators, because a post-measurement state, for example, is such a convex combination of pure states. Again, you can check that this has all the mathematical properties of a density operator. You can check that this has trace 1. You can check that this is positive semi-definite, okay? So this is a valid density operator. And now you can describe the measurement as a process or as an operation or as a map, right? So now you can describe, let's say, the measurement of this observable A as a map that takes you from density operator rho sub psi, which is the density operator associated with the initial pure state, to the final density operator, which I've just called sigma. Okay, so this is a map or an operation from density operators to density operators. Okay, I hope this idea is clear. I'm just recasting what you already know about measurement. Of course, everything else I said up to this point is something you know, that it collapses a pure state into one of the eigenstates of the observable, but then we do not know what the outcome is, or you want to describe this whole thing as a process, right? From one input to an output, then you cannot be talking about the output every time in a conditional sense by saying that, okay, if outcome I was realized, then the state is ket AI. To avoid that, you can use this description where you can now describe the output as a probabilistic mixture of pure states, right? And that again is nothing but a density operator. And the measurement process itself can be described as a map or an operation. More, you can qualify this by saying that this is a quantum operation from density operators to density operators. Okay, so this is where I wanted to start today by talking about quantum operations on density operators. Okay, So we saw one example of this just now, which is measurement, right? But what we looked at last semester by and large was a very different kind of quantum operation, namely a unitary transformation, right? Because we said, well, states, I mean, the objects that you're going to use to compute are the quantum states, and those are vectors in some Hilbert space or some finite dimensional linear vector space. How can you transform these states? Well, you need to transform them in such a way that their norm is preserved. They have to be unit vectors going to unit vectors. And we said, therefore, that the kind of operators that satisfy this constraint are the so-called unitary operators U. They, of course, satisfy U dagger U, which is U dagger is identity, right? So they are norm preserving, right? And because they are norm preserving, well, not because. So because they're norm preserving, they map valid quantum states to valid quantum states, right? So this was the bulk of what we saw during last semester's discussion on quantum gates, circuits, etc. So these are the building blocks of your quantum devices. These are the quantum gates, right? Now, the way a unitary operator would act on a pure state is simply as U psi, giving you some other state phi. And then you know that inner product psi psi is the same as inner product phi phi, right? Because you just take the inner product from both sides and you can see this, right? How does a unitary transformation act on a density operator now? Because we have kind of seen that the more general way to describe a quantum state is not just using pure states, but using such convex combinations of pure states, which are also called density operators, right? So how does a unitary operator act on a density matrix? On a density matrix or a mixed state, if any of this is not clear to you, please stop and ask me, because this is just the basic stuff that we're still doing. So on a density operator or a mixed state, how does U act? It acts by conjugation, right? So if I have to say that, so I can draw a box like this, for example, and I can say there's a unitary operator here, and I would like to input a density operator here, or whatever that means. But just to, since we talk in terms of these boxes and circuits, what is the output in this case? It is simply U rho U dagger, right? This is what one means by acting by conjugation, right? So this is how, because remember the density matrix itself is an operator, and you want to know how does a unitary transformation act on the density matrix? Well, it acts in this fashion. Those of you who have done physics courses would have seen this plenty, right? Because your U comes from some underlying Hamiltonian. This describes, for example, time evolution in a physical sense, right? This is your time evolution operator, right? So I can think of rho at time t is equal to 0, transforming to some sigma at time t by the action of this unitary operator U rho U dagger, right? So now, how does the unitary operator act on a density matrix? The first question that you should ask yourself is the final matrix that you get. So remember, this is a matrix. This is another matrix. Is this final matrix that you get still a density operator? So is sigma still a density operator? What is trace of sigma? I'll drop the time description. I'll just say trace of sigma. What is this? This is trace U rho U dagger. What is this?
1.
Why is it 1?
Because trace is cyclic, so U dagger.
Correct, exactly. So this becomes rho. You can think of it whichever way. So trace is cyclic. So you can move things around. So this is U dagger U's identity. So this is the same as trace rho, and trace rho is 1 because we started in a density operator. So this, the fact that the final state has the same trace as the initial state is what we will call a trace preserving operation. Okay, this is a term that will often get used this semester. It's called a trace preserving operation. Of course, the measurement also is a trace preserving operation, right? It maps density operators to density operators, means it is a trace preserving operation, right? So let me note that here also. So this is also trace preserving. Oops. So even if we do not start from a trace one operator, right? Whatever is a trace of the initial state is the same as the trace of the final state, right? That's what a trace preserving operation means, is exactly this statement. That trace rho is the same as trace sigma. Okay. What is the other constraint? It must be a positive semi-definite operator. How do we guarantee that u rho u dagger is positive? How can you argue that?
When you multiply with psi, it becomes another pure state. U dagger psi becomes another pure state. So it comes down to psi prime.
Positivity of, yeah, okay, so good. Okay, so that's one way of arguing. So I'll show you two ways of arguing this. So one way is to say, okay, look at phi u rho u dagger phi, right? Now, what Aditya just said is that u dagger phi is another unitary operator acting on phi. So that's another pure state, right? Because you know that the unitary operator maps pure states to pure states. So then this simply becomes psi rho psi, where psi is simply u or u dagger acting on phi. And this is positive because rho is positive semi-definite. So u rho u dagger is positive semi-definite. This is one way of arguing this. Here's another way of arguing this. Because rho is positive semi-definite, I can write this as u square root rho times square root rho times u dagger. Okay, so basically I'm splitting rho like this, and I can do this because rho is positive semi-definite. I'll just say positive, but I mean positive semi-definite. Okay. There is a valid notion of a square root for a positive semi-definite operator. Once I do this, you realize that this is then of the form some matrix M times its adjoint. Okay. Is that clear? So this, if I call this matrix M, then this is its adjoint, right? Because square root rho is also going to be Hermitian. Okay, what do I mean by square root of an operator? It's because these are all Hermitian operators, the square root is easily understood, right? It is simply the operator whose eigenvalues are the square roots of the eigenvalues of the operator rho itself with the same eigenstates. So this is nothing but an operator of the form M dagger, and such operators are always positive. So this is a third fact about positive operators that you should all revise or revisit, that the expectation in any state is positive. The eigenvalues are all positive. Also, every positive operator can be written in this form. Okay, this is a particular decomposition of a positive operator of the form M dagger or M dagger M. Okay. Conversely, any operator of the form M dagger or M dagger M is going to be positive semi-definite. So this is a third useful fact that we should remember about positive operators. I wrote down two. Where was this? Yeah. Also, let me add to that list. Rho can be written of the form M dagger M. Okay. And in this case, in this particular case, the M and M dagger are simply the square root of the operator itself. Okay, because in this case, it's just, yeah. But in general, I'm saying that you can write this as, okay. So these are two ways of arguing that the final state that you have after a unitary transformation is also a valid density operator. So what are the two facts that we note about unitary transformations and measurements? So I'm going to say that these are both valid quantum operations. Of course, we knew that all along, right? But now I'm going to kind of cast this whole thing in an axiomatic way, right? I'm going to say we know that already these are valid transformations, right? Because these also come from the physics of the whole system, right? We know that measurement is a valid thing to talk about. We have worked out a way to describe it mathematically. We know that, of course, unitary transformations are valid transformations of quantum states. And I've just showed you how they act not just on pure states or vectors, but how they act on density matrices. So they are both valid quantum operations. And what are the two properties that we saw? Well, they are both positive maps. So what do I mean by a positive map? It's a map or a transformation that maps positive operators to positive operators. And they are both trace preserving, which means that trace of rho is the same as trace of whether it's a measurement map or the unitary map, right? The trace of the final state is the same, and they are both positive maps. You can think of this as positivity preserving maps, right? In the sense that they map positive operators to positive operators. So they are both valid quantum operations. So now this leads me to the next question. Are these the only valid quantum operations, or are there more general quantum operations? With these two properties, I seem to have abstracted out what the mathematical constraint that a general quantum operations should satisfy are, right? A general quantum operation will be a valid physical transform. I think someone has their I'm going to mute. I find it hard to hear the sound of my own voice. You guys don't have an option, but I can mute it. Okay, so what kind of properties should a general quantum operation satisfy? Well, what do I mean by a general quantum operation? It's any map, I'll just call a general map M, right? That takes density operators to density operators. So let me write it in words first. Any map from density operators to density operators. And I'm kind of arguing this in reverse in the sense I showed you two examples of this, and I'm now going to abstract out what are these properties that these two examples satisfied. In particular, they were positivity preserving and trace preserving. And once these two properties are satisfied, then it can be a valid quantum operation. But why do I need to look beyond unitary and measurement? Why do I need to even think about the existence of something beyond unitary transformations and measurements? Because of the following fact. Suppose this is all that there was, right? Suppose this is all that there was, that there were just measurements and unitary transformations. Then there is really no notion of noise, right? Why is that? Because a unitary transformation, so let me just note this here. Recall that a unitary transformation, so I can think of this operation itself as a map, right? So I can say this is u of rho is u rho u dagger, where u, this u, the Roman u, is a specific unitary operator, and this kind of curly u is to say that it's a map, just like how I wrote a curly m for measurement, and in general I will use curly m for maps, right? This unitary map is reversible. So it's always reversible. So if I take rho and I transform it like this, it's just a cartoon picture or a box or circuit picture, then I simply have to apply the unitary U dagger, right? Because if U is unitary, then so is U dagger, and I get back rho. So this you also know from your time evolution in quantum mechanics that this is always reversible, right? So then where's the notion of noise? So if I just had unitary transformations as my maps, and then there's of course measurement, which brings in a certain element of non-determinism, but that's about it, right? So there is no notion really of noise, right? So is this all that can happen to quantum states, or can there be something more beyond unitary transformations? Can there be some kind of irreversible transformations, right? Of course, already we know an example of an irreversible transformation, which is measurement, right? Measurement, of course, is not reversible. So even within this allowed set of quantum operations, we have seen two different examples. A unitary map, which is deterministic evolution, which is reversible because simply the adjoint of U is also a unitary matrix, and so this is a reversible operation. But then I also have measurement, which is an irreversible operation, right? So it can be of either kind. So the question really then becomes, are there other irreversible operations which are possible? And the answer is of course yes, and that's why we even have the next few weeks of lectures and an entire research area based on this. The point is that these two properties can be abstracted out to define a general quantum operation. So let me now write this out formally, right? So there are some other properties that we must include in this, things like linearity and so on. I have just picked out the two main operational parts, which is that it preserves positivity and it is trace preserving. But mathematically, there's a few more things that we can write down. So first of all, I'm going to throughout this course represent this set of density operators using some notation. So let me say, I'm going to say S of, so let's say that we are in a, so consider a d-dimensional quantum space, okay? So consider a d-dimensional quantum system. So let's say that H is the associated Hilbert space. It's just a complex linear vector space at this point with an inner product, right? Then we can think about the set of positive, see, I often use positive and positive semi-definite interchangeably, okay? And in 99.9% of the cases, there'll be no issue. There may be some, issues somewhere, but we'll see. When it comes to that, I'll be a bit more precise. But when I say positive, I mean, okay, I can add semi-definite here instead of giving such a big disclaimer, okay? So set of positive semi-definite trace 1 operators on H. Okay, so by S, I simply mean the set of valid quantum states of H, right? And the set of valid quantum states is not just the set of unit vectors, but it is the set of positive semi-definite trace 1 operators on H. This includes the unit vectors because we can also write down the density operator associated with a pure state, right? Okay, so now I'm looking for the general properties of a quantum operation. So I'm going to call these as E. Okay, I know I wrote it as M, but let me change that to E here as well to be consistent. So let me say E. Properties of a quantum operation E, which acts from the set of density operators to the set of density operators on H. To be very mathematically precise and pedantic, I could have a different Hilbert space K at the output. and I could map from density operators on one space to density operators on a different space, right? But again, that's a simple enough generalization that we can stick to only talking about this case where we go from the set of positive trace 1 operators on H to the set of positive trace 1 operators on H, right? So the properties that we need such that it represents a physical process, right? Because we want to look at the mathematical characteristics of a map which can describe quantum noise. And of course, quantum noise is something that is real and physical, right? It is not a mathematical construct. So what are the mathematical constraints that it must have such that it can represent a physical process? Firstly, must be a linear map. Both unitary and measurement are linear transformations, right? Okay. Second, must be positive. E must be a positive map. And I already defined what this is, but I'll state it again. It maps positive semi-definite operators to positive operators. But it turns out that just positivity doesn't suffice. Okay, and we need something called complete positivity. So I'm going to write that next and I'm going to define it shortly. E is a completely positive map. And finally, E is trace preserving, which means E of trace of rho. Oops, I meant trace. Yeah. Trace of E of rho is the same as trace of rho. Positive map simply means E acting on rho is also positive semi-definite if rho is positive semi-definite. Okay, so these two properties I've already shown you with examples. So I hope you understand these two properties well. Now, what is this? What does it mean to say that a map is completely positive? Okay, so let's define this formally. And I will often shorten this as CP. The trace preserving, I will often shorten it as TP. Okay. So we say that E is CP if, and only if you can say, E tensor, the identity map, is positive for all rho which belong to this set of density operators on H. And I mean positive semi-definite. Okay. So what do I mean by this now? So you imagine that I have, so again, let's go back to this box picture. I have this density operator. I have E and I have E of rho, right? This is the map E that one is talking about, the general quantum operation. But now what I'm saying is the following, that suppose rho is not an isolated system. Suppose rho is actually part of a larger system like this. But you are not doing anything to the other half of this tensor product, which means this is an identity map, right? You understand? So my input is actually some kind of state which belongs to a larger space. So this could be H tensor K, for example, right? So this belongs to the set of density operators on some H tensor K. So my input is actually of the form rho tensor sigma, which belongs to the set of density operators on H tensor K. But this operation, quantum operation, or this map acts only on one half of this bipartite system, right? then you would say that the complete map on the full system is of this form. It's E tensor identity, and it's tensor because you see I've not joined these two boxes. So it's acting independently. So E is acting just on this subsystem of a larger system, right? And then I'm looking again only at the output. So all of you remember the partial trace idea, right? So I can talk about just the density operator on this subsystem. I can again talk about the density operator on this subsystem, whatever it is here, right? Now, even in this scenario, right, even if my E acts only on one half of this kind of a tensor product system, right? In this case, I put a tensor product here, but okay, let me just draw a more general picture. Now, if this is the case, it is clear that this output state is going to be positive, right? Because this is just identity acting on sigma. So I can break this down. So let me just write this out formally. So I have the map E tensor I acting on rho tensor sigma. This becomes E acting on rho tensor I acting on sigma. And of course, this is positive semi-definite, right? Because E is positive, okay? But where complete positivity becomes non-trivial is when this input out here is not of this product form, but it is of an entangled form. So let me write down something like this. So the input is product is the simple case, and this is a simple case in which complete positivity is naturally satisfied. Because what does complete positivity say? Not just E of rho is positive, but E tensor I acting on rho tensor anything, or E tensor I acting on this larger system is always positive, right? So I can think of a scenario where I have my input, although I put two wires here, that this, for example, is one of the so-called Bell states, right? So this is a different example where the input is entangled. I hope everyone remembers at least that there exist these entangled states called Bell states, right? And I hope everyone remembers the idea of an entangled state. In this case, the input is a pure state, right? And once again, you have map acting only on one half and identity on the other half. But now this output again is not factorizable because what you have as the input is an entangled state, right? So the output may or may not be factorizable. So you have to now write the output in this way, right? That it is beta 0, 0, beta 0, 0. So what is this? So this is a qubit example, right? So beta 0, 0, remember, is simply this state, 0, 0 plus 1, 1 over root 2. Okay. So this is now an entangled input. And of course, you can write down what the reduced state here is. But the point is that this is now acting on an entangled input. This output state, whatever it is, must also be positive. And only then is the map considered to be completely positive. Okay. And the way I've explained it, the motivation for this mathematical constraint should be clear. Because what I can have is not just pure states, not just individual states that this map must act on. It must also act on states which are correlated with other systems as inputs, right? It must also be a valid map, a valid physical process when it acts on these kind of entangled inputs, right? So let me back up here and state this like this. So it's positive semi-definite for all, let me say rho, I should say, I'll just call this rho AB on some HA tensor HP. Okay, that's the correct way of saying this, because I'm now talking about bipartite density operators that act on multiple systems, right? And the map is just acting on one half of this, and still the action of this map must be completely positive. Once again, this is automatically taken care of if you think about measurement and unitary transformation. If this E were just a unitary transformation, this is always taken care of. Remember when we did this in circuits last year, we said these are local unitaries, right? If I just had replaced this E by a U, that's just a local unitary gate acting on one half of a entangled state. But now I'm talking about more general maps, and for more general maps, it turns out that this property is not always true. And so it must be stated as a constraint, and we must only look at those set of maps which satisfy this constraint, that the action on any entangled state or the action on a state which is a part of a larger system, right, which is only a subsystem of a larger system, that final state must also be positive. Okay, so let me now just state here that there are maps that are positive but not completely positive. I know that we did not get to cover this during our QCQI course, but have people heard of any kind of map like this? Does anyone in the class know of an example of such a map? Have you come across this? Anybody who's doing project on entanglement? Entanglement detection? No? Okay, so the example of this, and one prime example of this, is what is called the partial transpose map, or just the transpose map. Okay, so what is a transpose map? So if I take a density matrix, I can write down its transpose. It's just the transpose of the matrix, right? So I define a map T, okay, which is simply the transpose of a density matrix. Right? So if rho is positive, then it is easy to show. So check this. If rho is positive, then rho transpose is also positive. Okay. But if you do a partial transpose, so I will now call this T sub A of rho AB, where it's understood that there is now two systems in play, HA tensor HB. Okay. And I'm doing a transpose only within subsystem A. Okay. Then the partial transpose map, the final state that I get is not always positive. Okay. So when transpose becomes a partial transpose, it loses the positivity property. The final state, the final matrix that I get, the final operator that I get is not a valid quantum state. So the partial transpose cannot be a valid physical operation. So I'm not going to define what partial transpose is exactly and so on. I'm just giving you an idea that this is basically transpose within one of the two subsystems that this density operator is a part of. We'll come to this again when we discuss entanglement theory, but I just wanted to mention here that there are indeed maps which are positive. So long as they act on a single system, it's a valid map. It can be thought of as a valid physical process, but then the minute you act on when your state is part of a larger subsystem, a larger system, then it is no longer physical. So a transpose map will not fit into our category of valid quantum operations. Okay. So this is just to show that there are examples of such things which are positive, but not completely positive. I'll see if I can throw this in the assignment a little bit, and then we'll revisit this when we discuss entanglement theory. Because based on this, you can actually detect, you can use this to witness or detect entanglement, right? So partial transpose is not a valid physical operation. So let's recap quickly all that we just said. A valid quantum operation is a completely positive trace preserving map from the space of density operators to space of density operators. So this is often abbreviated as a CPTP map, right? And what we have stated is the most general mathematical form, right? Because we have taken care of all the physical constraints. We have taken care of the trace being one. We have taken care of the positivity part. We have even taken care of the complete positivity part, that not just is the action on a given density operator positive, but when the density operator is part of a larger system, so also the map is positive, the action of the map is positive. So that then encapsulates a CPTP map. So whatever goes by the name of quantum noise or a quantum noise channel has to be within this category of CPTP maps. So we already saw two examples of transformations which are CPTP maps. Measurement is a completely positive trace preserving map. Unitary transformations are, of course, completely positive trace preserving maps. But the third category, which we have not explored so far, is what we will study in the next few lectures, is the so-called quantum noise channel. So what, can describe something which is, so this in some sense subsumes both of these. So both what we call a quantum channel and a quantum noise channel many times, because that's what we're interested in. This includes the class of measurement transformations. This includes the class of unitary transformations, except of course a single unitary transformation is reversible. So it's really not noise, but there is something beyond unitary transformations, which goes by the name of quantum channels, which satisfies mathematically. This is what it is. It's a completely positive trace preserving map. So I think I will stop here. This being the first lecture, I don't want to load you too much. And I also reviewed some of the earlier things. So let me stop here and ask you if you have questions.
Yes, ma'am.
Yeah.
If we are mentioning the condition of complete positivity, right?
Yeah.
Does it in itself include positive condition, like where you mentioned properties that needs to be satisfied point-wise, right? Second, isn't second point the part of third point, which is like more general?
Yeah, indeed, you're right. So that is why finally, when I state what a quantum channel is, I don't say positive and completely positive. I only say completely positive and trace preserving, right? So of course, complete positivity includes the class of positive maps, right? But not every positive map is completely positive. And that's the reason that I separated it out, because our physical intuition tells us that 2 must hold, right? But where did 3 come from? So that 2 must hold is clear, and that's why it's good to mention it. It's useful to mention it, and it's much more easy constraint to visualize. Complete positivity becomes a little bit of a leap from that. And so that's why I mentioned it separately. You're indeed right that once I mention 3, 2 becomes redundant, right? So because all completely positive maps are positive. But of course, the converse is not true. As I just mentioned, there's this example of the transpose map, which is positive, but not completely positive. Okay. Yeah. So we will only say completely positive and trace preserving for a general quantum operation from here on. Yeah.
Ma'am, so when we define completely positive, we defined as like E tensor product I, right? Like the map acting on one subsystem and the other subsystem will be. So like if we have 2 maps, is it equivalent to saying like both should be completely positive if it is like what I'm asking is
yeah, if the second, it is a different map acting on the second subsystem. That's what you're saying, instead of identity. Yeah, that would be a valid map if and only if both the maps are completely positive. So I can give you maybe a pictorial visualization of this. So you can think of, I often draw these cartoon pictures for Hilbert spaces. So think of a big Hilbert space which is partitioned into two. Okay, so this is my HA and this is my HP. Now, although I draw this line, I hope you realize that there will be states which are crisscrossing this line in the sense that there will be correlated or entangled states across the subsystems, right? Now, it's possible that I have a map that acts only on A, okay? But such a map is physical only if its extension. So think of a map which acts only on A is EA, but the extension of the map on the full space, which is H, right? So on the full space, it should be of the form EA tensor IB, right? That's what I would say is an extension of this map on the full space. This should be a positive map, which means its action on any density operator in the full space, where H is HA tensor HP, right? On the full space, this should be positive. Similarly, you can now think of another map EB, which acts only on B. And once again, the extension on the full space, yeah, will be identity on A tensor EB. And this acting on any bipartite density operator should be positive. And then this will be valid. EA tensor EB will also be a valid quantum operation. Will be a valid map. Yeah, will be CP. Good.
Sure.
Okay, so tomorrow we'll look at this was somewhat abstract, right? This idea of CP and TP, but it turns out that such maps have a very nice representation in terms of a finite set of operators. That's what we'll look at tomorrow, and we'll also look at some physical scenarios where this general form of CP-TP map can arise. Okay, so I'll stop here, and I'll see you all tomorrow at 3:25.